Welcome everybody. So today's class we will see how to analyze a portal frame with the side sway subjected to vertical loads and columns of equal height. So this is your given problem. So two conditions, okay? It's a portal frame. The columns are of equal height and it is subjected to vertical loads. Here we have one vertical load 20 kilonewton acting at a distance of 5 meter from B. The frame A, B, C, D, the columns are A, B and C, D. The columns are of 10 meter height and the beam BC is 20 meter span. So this is a portal frame. Now there is a concentrated load of 20 kilonewton at a distance of 5 meter from B. Now when you come to the moment of inertia, for the column AB, the moment of inertia is considered as 2I. For BC, the moment of inertia is 6I. And for CD, the moment of inertia is I. So two conditions. Because the characteristic changes, that is moment of inertia changes, the frame will be subjected to side sway. Also, since the loading is not eccentric, also this frame will be subjected to side sway. So now we will see how to analyze this frame using Canny's method. So this comes under portal frames with side sway. And when we come for Canny's method, this comes under portal frame with a side sway, portal frame with vertical loads and equal height. We will see how to solve such problem. So step 1, as usual, we have to find the fixed end moments. So we know fixed end moment depends upon the external loadings. So here for the columns A, B and C, D, we do not have any external loadings. So the fixed end moment for the span AB will be 0. So MF AB is equal to MF BA is equal to 0 because there is no external loadings in the column AB. When you come for the beam or the span BC, you have an external loading of 20 kilonewton. So we know when you have a span, when you take the section, the supports, at these supports, we will assume the end as fixed supports. So when the ends are fixed supports, there will be negative moments. So when you are considering this section, XX, the left anti-clockwise will be negative and the right clockwise will be negative. So these both are hogging moments. So anti-clockwise, we will consider it as negative and clockwise, we will consider it as positive. Because left anti-clockwise moment is hogging and right clockwise moment is hogging. So anti-clockwise we will take it as negative and clockwise we will take it as positive. And when there is a concentrated load, the formula will be in the left it is minus WAB square by L square and at the right end it is plus WA square B by L square, where A and B are the distances taken from the point of application of load to the supports. So for the span BC, M of BC is minus WAB square by L square, minus W is 20, A is 5, B is 15, square by L is 20. 20 square we get minus 56.25 kilonewton meter. Similarly, M of CB is equal to plus WA square B by L square. W is 20, A is 5 and B is 15. So 5 square into 15 by 20 square we get plus 18.75 kilonewton meter. Now, for the column CD, M of CD is equal to M of DC is equal to 0 because there is no external loadings acting on CD. Now, we will move on to the second step. Step 2 is we have to find the rotation factors. So, we know rotation factor is nothing but minus half of the distribution factor. That is minus 0.5 times the distribution factor. So, when we consider, so this distribution factor and rotation factors are determined for the joints. The joints where more than one member meets. So, we have joints B and C where more than one member meet. And in order to find the stiffness factor, we know stiffness, relative stiffness. We know if the far end is fixed, the relative stiffness is I by L. And if the far end is hinged, the relative stiffness is 3 by 4 I by L. Here, everywhere it is a fixed support. So, it is I by L. So, only I by L is considered. So, we will consider the joints B and C. So, at the joint B, we have the members BA and BC. So, BA and BC. At the joint C, we have the members CB and CD. Now, everywhere it is fixed, right? Intermediate supports are also considered to be fixed supports. So, B and C are also considered to be fixed supports. So, BA, when you consider for the member BA, it is I by L. So, for BA, I is 2I and the length is 10 meter. So, 2I by I is 2I. So, 2I by 10. For BC, also it is I by L. Relative stiffness is I by L. So, here the member property is 6I. So, I by L is equal to 6I by the span length is 20 meters. So, 6I by 20, we get 3I by 10. So, similarly, for the joint C, for the members CB and CD also, it is I by L and I by L. Same way, you calculate. Now, we will consider the sigma k, that is a summation of the relative stiffness at every joint. So, 2I by 10 plus 3I by 10, we get 5I by 10, that is I by 2. And at joint C, it is 3I by 10 plus I by 10, we get 4I by 10, that is 2I by 5. Now, we will determine the distribution factor. So, distribution factor is equal to K by sigma K. So, distribution factor for BA is 2I by 10 multiplied by 5I by 10. Sorry, 2I by 10 divided by 5I by 10. We get 2 by 5. Similarly, 3I by 10 divided by I by 2. We get 3 by 5. Similarly, you can calculate the distribution factor for joint C. We get 3 by 4 and 1 by 4. Now, we can add. See, if you add this, you should get 1. Add this, you will get 1. Okay. Now, from distribution factor, we will find the rotation factor. So, rotation factor is equal to minus 0.5 times the distribution factor or minus half of distribution factor. So, minus half of 2 by 5, we get minus 0.2. Minus half of 3 by 5, we get minus 0.3. Minus half of 3 by 4, we get minus 0.375. And minus half of 1 by 4, we get minus 0.125. Now, you can add this. You should get minus 0.5. Add these both, you should get minus 0.5. Okay, now we will move on to step 3. So, step 3 is displacement factors. Since here it is subjected to side way, in addition to rotation factor, we have displacement factors and displacement contributions. Okay, so rotation factor and corresponding rotational contributions. Similarly, displacement factor and corresponding displacement contributions. So, since there is a side sway, there will be displacement. So, we know how the sway occurs. See, sway will be occurring like this, right? So A, B, C, D, this BC will be shifted to B dash and C dash. But the displacement is happening at the joints B and C for the columns, okay, that is for AB, BA and CD. So you will find the displacement factor for the column BA and for the column CD. Okay, so we know for portal frames with the columns of equal height and vertical loads, we have studied in the last class, previous class. For columns with equal height and vertical loads, the displacement factor Dij, that is for the column B, A, B, this Ij can be B, A. Okay, so this BA, this is equal, that is displacement BA will be equal to displacement factor BA, and displacement factor AB will be same. So Dij will be equal to minus 1.5 into, this is stiffness factor, relative stiffness, Kij divided by sigma r Kij. Sigma r is nothing but the story. So sigma r means it is a combination of, the sigma means the summation of the columns, that is BA and CD. Okay. So you can see here displacement factor dBA will be equal to, see this is also equal to DAB. Both are same. Okay. Minus 1.5 into Kij, that is KBA. Ij means BA, right? So KBA divided by the columns, summation of the stiffness of the columns, KBA plus KCD. So you get minus 1.5 into KBA is, for BA, it is 2I by 10. So 2I by 10 divided by KBA is 2I by 10, KCD, CD is 2I by 5. 2I, KCD, sorry, this I by 10. This I by 10. So we get minus 1. Similarly, displacement factor DCD will be equal to minus 1.5 into KCD divided by KBA plus KCD. So we get, substitute, we see only this value is changing, right? KCD is I by 10. Remaining things are same. So we get minus 0.5. So now you can see the factor is minus 1.5. If you add these both, you will get minus 1.5. Okay. So we will move on to the next step. So here, listen, while you are doing the step 2, in addition to the rotation factor, you have to find the displacement factor also. That is the additional step coming here for analysis of frames with the side sway. Now we will move on to our fourth step, that is resultant restraint moments. So we know resultant restraint moments are nothing but the summation of the fixed moments joining at the joints. So here we have two joints B and C. So for B and C we will have resultant restraint moments. So resultant restraint moment at B is M of B, that will be equal to fixed end moment for the span BA and fixed end moment for the span BC. So M of BA plus M of BC. We have calculated these values in our step 1 fixed end moments. So we get minus 56.25 kilonewton meter. Similarly, MFC fixed end, that is a resultant restraint moment at C, will be equal to M of CB plus M of CD. M of CB plus M of CD. That is equal to plus 18.75 kilonewton meter. Now we will move on to our fifth step. Fifth step is drawing the Canni's table, Canni's iteration cycle. Okay. So this is our fifth step. So for Canny's iteration cycle, we know how to draw the iteration cycle. For every joint, you have to draw one small circle and another larger circle, or one small square and another larger square. So this is joint B and this is joint C. We have the columns A and D, right? So from B, we have the columns A, and here we have the column D. Now, inside the smaller box, we will write the resultant restraint moment which we have obtained in our fourth step. So resultant restraint moments are for joints B and C. So the resultant restraint moment is minus 56.25 for joint B, and for joint C it is plus 18.25. So we have obtained this in our fourth step. Now we will write the fixed end moments. So we know the fixed end moments. We know the fixed end moments. MF AB is 0, right? Fixed end moment M of AB is 0. M of BA is 0. M of BC is minus 56.25. M of CB is plus 18.75. M of CB okay, this is 18.75. This is not 18.25, 18.75. Okay, for M of CD is 0 and M of DC is also 0. Listen, that is why this is a summation of minus 56.25 plus 0, we get minus 56.25 plus 18.75 plus 0, we get 18.75. Now we will write the rotation factor. So rotation factor we have obtained in our second step. So we know the rotation factor is, for BA the rotation factor is minus 0.2. For BC the rotation factor is minus 0.3. See, the rotation factor should be written in the larger square. Rotation factor for the joint C for the member BC is minus 0.375. And for the member CD, for CD the rotation factor is minus 0.125. Now we will write the displacement factor. So the displacement factors are for the columns BA and for the columns CD, right? For the span, for the column BA, the displacement factor is minus 1.0. For the column CD, the displacement factor is minus 0.5. Okay. So these things you have to write first. So draw the cycle. First of all, write the restraint moments, write the fixed end moments, write the rotational factors, and write the distribution factor. Now we will find the values of iterations. So we know The rotational contributions are represented by small m and the displacement contribution is represented by m dash. Small m means rotational contribution and small m dash means this displacement contribution. So, the rotational contributions will be for the joints BC, right? Since A and D are fixed, there will not be any rotational contributions from A and D. Only from B and C we will have the rotational contributions. So, the rotational contributions are, you will have M BC. From here we will have the rotational contribution M CD. So at a joint B we will have MBC and MBA. Okay, MBC and MBA. For the joint C you will have rotational contributions MCD and CB. This is a CB, MCB and MCD. Okay. See, if there is no rotational factor, there will not be rotational contributions. In simple, okay. Here we have the rotational. See what are for the members we have rotational contributions. We will have rotational factor. We have rotational contributions. Similarly, the displacement contributions. So displacement factor is for BA and for CD, right? For the joints B and C, that is for the columns. So M dash BA. So we can write it M dash BA. I will write it in the other way. So this is for the columns. So it is M dash BA. And here it is M dash CD. See, you write it horizontally, okay? It's hard for me to write. So I will write it here. M dash of BA and M dash of CD. Okay, we will write horizontally. Okay. Now, we will calculate the values. So we have to calculate the rotational contributions and displacement contributions. So we will go on to step 6, Canny's iterations. Okay, step 6, we have two joints, joint B and joint C. So joint B, we have rotational contribution and displacement contribution. Joint C also we have rotational contribution and displacement contribution. So first joint B, we will find the rotational contribution. So here the rotational contribution is RBC, that is rotation factor multiplied by the fixed end moment plus rotational contributions plus displacement contributions. I repeat, MBC will be the rotational contribution at joint B. So that will be equal to rotation factor at joint B for the member BC, right? This is rotational contribution at B for the member BC. Rotation factor for the at B for the member BC multiplied by fixed end moment plus rotational contributions plus displacement contribution. Displacement contribution. So fixed end moment. This is not fixed end moment, restrained moment. Restrained moment at B plus rotational contributions. So B, at B we have BC and BA, right? So for B, at joint B, we have rotational contributions M's from the nearer joints, that is M's CB from the joint C, that is CB, and from the joint A, AB, plus we will have displacement contribution from the nearer members. So for B, the nearer member is AB, right? That is column. Displacement is for column. So we will take BA. Now, this RBC is same, right? So RBC is 0.3 minus 0.3. RBC is minus 0.3. This is not going to change. Similarly, okay, this RBC is not going to change and RBA is not going to change. So RBC is minus 0.3, RBA is minus 0.2. Similarly, MFB and MF, this is also not going to change. So MFB is minus 56.25, right? Minus 56.25. Minus 56.25. But these values changes. So how these values changes? Depending upon the iterations. So first of all, initially we will assume this as a 0, all these values as a 0. For the second iteration, you will take the values from the first iteration. Okay, so the procedure moves on like that. Now, when you are coming to displacement contribution, the formula is m dash ij is equal to dij into sigma r into mij plus mji. You have studied this in the last class. So dij is distribution factor for the column BA. That is, at joint B we have only one column BA. So distribution factor for the column BA, and this distribution factor is minus 1. This is not going to change, minus 1. Okay. Now, Mij is nothing but for the first column. Mij means first column. Mji is second column. So Mij means MBA plus MAB, and Mji means it is the second column, that is MCD plus MDC. R means this R means the story. So sigma R means the displacements of all the columns corresponding to this story. Okay. Now, for the first iteration, we will move on to the first iteration. So for the first iteration, the rotational contribution MBC will be equal to minus 0.3 multiplied by minus 56.25, and these things remains 0 because this is the initial iteration. So we get, for the first iteration, we get MBC is equal to plus 16.88. For the second iteration, for MBA, it is minus 0.2 into minus 56.25 plus these values remains 0. We get plus 11.25. Now, M dash BA is equal to minus 1 into MBA. See, MBA we have calculated now. MBA is calculated. Sorry. See, after finding the rotational contributions, we have to come for displacement contributions. So now rotational contribution for joint B is over. Now we will go on for rotational contribution for joint C. Okay. For joint C, the rotational contribution will be, the formula will be RCB multiplied by MFC plus the contribution from the nearer joints. So if you take joint C, the nearer joints are MBC, right? So rotational contribution from the nearer joint MBC plus rotational contribution from the nearer joint MDC plus the displacement contribution of the nearer column, that is M dash CD. Similarly, MCD is equal to RCD multiplied by the remaining things is the same, MFC plus MBC plus MDC plus M dash CD. Now, see this M here, okay, we will find this. So, RCB is minus 0.375, right? Minus 0.375 and RCD is minus 0.125. MFC is plus 18.25. So, plus 18.25. The remaining things we will take from the previous iterations. So, what is MBC now? MBC we have calculated it as plus 16.88. So, what we get is minus 0.375 multiplied by plus 18.25 plus MBC is 16.88 DC. See, DC means the rotational contribution from the joint D. This is always 0. Here also, the rotational contribution from the joint A is always 0. Okay, this is always 0. So, similarly, this is 0. So, we get M dash CD we have not calculated, right? We have not determined. So, this will be taken as 0. So, value for MBC is plus 16.88. So, calculate, we get MCB, that is rotational contribution, MCB is equal to minus 13.17. Similarly, MCD is equal to minus 4.39. See, for both the cases, this is 0 for the first iteration, MBC. The value is MBC is equal to plus 16.88. Okay. Now we will calculate the displacement contributions. So, displacement factor dBA is minus 1. MBA, the value is plus 11.25. Okay, MBA is plus 11.25. MAB is always 0. Similarly, MDC is always 0. So, MBA is plus 11.25. MCD is minus 4.39. So, substitute, we get M dash BA is equal to minus 6.86. Similarly, displacement contribution M dash CD will be equal to DCD, displacement contribution, into MBA plus MAB plus MCD plus MDC. So, these values are always 0. Displacement contribution, displacement factor CD is minus 0.5. So, this is minus 0.5. MBA, you can take from the first step, MBA first iteration plus 11.25. MCD is minus 4.39. So substitute the values. We get m dash CD is equal to minus 3.43. So first iteration is over. Similarly, you can move on to the second iterations. You can solve it. See, for the second iteration, you have for MCB you have to use the value minus 13.17. M dash of BA, we will be using the value M dash of BA. You will be using the value minus 6.86. That is, you have to use the values what you have obtained at the last step or the last iteration. That you have to use for each calculations. Every time you have to use the values which you have obtained at the end. Okay. So you can solve it. So you get for the second iteration, so you can continue it up to iterations 5. So I will write the values in the Canni's cycle. You have to calculate it here and you have to write the values. Okay, I will write the values. You please check it. Hope you understood. See, every time the formula is the same. The constant values I have given you, these values are not changing. These rotational contributions and displacement contributions changes for every iterations. Whatever you have obtained in the last iteration, you have to use it for the present iteration. So we will get the values as MBC. See, for MBC, that is rotational contribution for BC. MBC, the values will be, for the first iteration it is plus 16.88. Second iteration is plus 22.84. Third iteration plus 24.28. Fourth iteration plus 24.52. Fifth iteration plus 24.56. For MBA, the first iteration it is plus 11.25. Second iteration plus 15.26. Third iteration plus 16.18. Fourth iteration plus 16.35. Fifth iteration plus 16.37. Now MCB, the first iteration, the value is minus 13.17. Second iteration minus 14.12. Third iteration minus 13.97. Fourth iteration minus 13.88. Fifth iteration minus 13.86. For MCD, the first iteration it is minus 4.39. Second iteration minus 4.71. Third iteration minus 4.66. Fourth iteration minus 4.63. Fifth iteration minus 4.62. So rotational contributions are over. Now we will go for displacement contributions. So the displacement contributions are M dash BA for M dash BA, the values are minus 6.86. First iteration. Second iteration minus 10.55. Third iteration minus 11.52. Fourth iteration minus 11.72. And minus 11.73. Fifth iteration minus 11.73. For M dash CD, first iteration minus 3.43, minus 5.28, minus 5.76, minus 5.86, minus 5.87. Okay, now you can finish your iterations. Now, so the final values for the rotational contributions and displacement contributions. So we have completed step 6, right? See, step 7, you can write the values of your rotational contributions and displacement contributions. That is MBA. MBA is the last value, what you have obtained at the last iteration, that is plus 16.37. MBC. MBC is plus 24.56. MCB is minus 13.86. MCD is minus 4.62. M dash of BA is equal to M dash of AB is equal to. See, both are same for displacement contribution. That is for the columns. Okay. So at B and at A, both are same because displacement contribution is considered for columns. Minus 11.73. And M dash of CD equal to M dash of DC will be equal to minus 5.87. Now we will write the final moments. We will take it as step 8. Step 8 is final moments. So final moments okay. So final moments, we know this Canny's iteration cycle is an extension of slope deflection equation. So we know the slope deflection equation MAB is equal to MFAB plus 2EI by L into 2 theta A plus theta B minus 3 delta by L, right? So actually this is AB, this is BA and this is delta AB. So this can be written as MFAB plus 2 times MAB plus MBA minus M dash of AB. This is the meaning of that, right? Now, we will open up a tabular column. So for finding these, so in general, you can write this as Mij is equal to Mfij plus 2Mij plus Mji minus M dash of Ij. Now we will open up the tabular column. So our final end moments Mij. Mij, we have Mfij, then 2Mij, Mji, Mij, Mij. So finally we will get Mij is equal to, if this is 1, 2, 3 and 4, it is 1 plus 2 plus 3 minus 4. Okay. So we have MAB, MBA, MBC, MCB, MCD and MDC. Okay. So MFIJ for AB, it is M of AB, right? So what is M of AB? M of AB is 0 to MAB. So MAB is 0, right? MAB is 0. MDC is also 0. There is no rotational contribution from the joint A and D. So 2MAB is 0. MBA, J means B, right? I is A. So MBA, MBA is plus 16.37. So plus 16.37. This is M dash. M dash of IJ, M dash of AB is minus 11.73. Minus 11.73. So we get plus 16.37. Okay, sorry. See, what you have obtaining here is minus M dash IJ. So you have to add all these. Actually, what we are obtaining here, the distribution contribution is the negative values only. Okay, so there is no need of considering this minus sign. If it is minus, so otherwise I will tell you, see, this is the distribution contribution. This is okay. This minus 6 plus. Okay, the reason is, say I made a mistake. This is minus that M dash AB is minus 6 EI del AB by L square. Okay, so here it is actually plus. So it is 1 plus 2 plus 3 plus 4. So what we get is MAB is equal to plus 6 point, plus 4.64. Similarly, for MBA, fixed end moment is 0 to MIJ, that is MBA. We know MBA is plus 16.37. So plus 16.37 multiplied by 2, we get plus 32.74. Then MJI, that is small MAB, rotational contribution MAB is equal to 0. Okay, so 0. M dash IJ is equal to minus 11.73. So adding all, you get plus 21.01. Now we will move on to MBC. So similarly, MBC is minus 56.25 plus 49.12 minus 13.86. We get minus 20.99. For MCB, the fixed end moment is plus 18.25. To MCB is minus 27.72. MBC is plus 24.56. M dash CB is 0. So we get plus 15.09. MCD, M of CD is 0. 2MCD is minus 9.24. MDC is 0. M dash CD is minus 5.87. We get minus 15.11. Now MDC, MFDC is 0. 2MDC is 0. MCD is minus 4.62. M dash DC is minus 5.87. It is minus 10.49. Now we will draw the, so this is our moments. These are our final moments. Kilonewton meter. Okay, these are our final moments. So while drawing the bending moment diagram, we will draw the simple beam moment diagram first. Next, when you are considering AB, this is A and this is B. See, AB, it is positive, clockwise. BA, again clockwise. Okay. So when you are drawing the bending moment diagram, this will face towards the right and here it will face towards the left. Now, this is AB, BC. For BC, it's anti-clockwise, minus 20. So, anti-clockwise pointing upwards, clockwise pointing upwards. So, you get minus 20 and plus 15. So, sign is not needed here because we are drawing the bending moment diagram upwards. Now, for CD, it is minus 15.11 minus 10. So, anti-clockwise, anti-clockwise, pointing towards the right and pointing towards the left. So, this is how you will draw the bending moment diagram. And for simple beam moment diagram, at there is a, how much? There is a 20 kilonewton load acting at a distance of 5 meter. So, it will be like this. So, the value is WAB by L. Okay. So, now we will draw the bending moment diagram. So, I will not go backwards for reference. Just we will draw the bending moment diagram here. So, for bending moment, there is no need of support, right? Okay, first of all, drawing the simple beam moment diagram. This W, simple beam moment diagram, it is WAB by L. So, W is 20 into 5 into 15 divided by 20, we get 75 kilonewton meter. So, here it is a 75 kilonewton meter. Now, for the span AB, okay, it is like this, 4.64, 21.01. Four 4.64, 21.0. Four 4.64, 21.0. Here also it is 21.0. Here it is 15.10. 21.0, 15.10. Here it is 10.49. And here it is 15.10. Okay, so this is our bending moment diagram. So the net bending moment diagram is okay. That is all. Thank you for listening. We will see the next problem in the next